Hey everybody, this is Larry. This is me going with Q4 of the weekly contest for Fitty. Oops, spoiler alert. Minimum rated subgraph with the required paths 2. Hit the like button, the subscribe button, join me in Discord. Let me know what you think about this one. So this one, it's not a hard problem if you have the template. And I could go over the explanations real quick, but I'm not gonna go over some of the implementation detail just because it is a little bit silly. In the sense that if you have to write templates, this is a 5-minute problem, maybe even less, honestly. Like, I know people probably did ChatGPT and cheating anyway, but the like, you could see someone doing it in 5 minutes, and a top person you could see it doing like 2-3 minutes, right? And I'll go over the explanation in detail. But maybe not the implementation for that reason, at least not in super detail. I mean, we'll still go over it. But yeah, let me bring up the drawing board real quick. And okay. So for this problem, there are a couple of things you need to know. And I'm going to explain it in the way that I figure out what components I needed. So I know that maybe, and I'm trying something new this time because I think if you explain it from the components and how you get from like A to B, yeah, okay. I think like that's one way to think about it. But for me, it's more like I was thinking backwards of, okay, I wanted to do this, I need this, and because I need this other thing, right? So I'm kind of working from it backwards, and that's how I think about solving this problem. And it may, I don't know, maybe it's less understandable in the sense of like it has is a tougher flow, but I think it is easier to see how you would come up with that solution, right? So okay, so let's say let's say we have some graph like this. Actually, yeah, maybe I'll just draw my own, yeah, right? Yeah, so let's say you have some graph, it's just nodes, right? Oops. Right, I don't know. I mean, it's fine, right? So the thing that we're asking to solve, and we have to do it in a fast, quick way, is just that, okay, given 3 nodes, basically, you have this node and maybe, I don't know, this node, and then maybe a destination node, right? So then here, we're trying to minimize the subgraph or subtree that contains, that allow us to go from here and here, right? In some way, I guess technically. I mean, you draw it this way, but you know what I mean, right? And so the idea here for me is a very visual one, right? The idea for me is that, okay, well, it's a tree, so there's a simple path for every 2 nodes, right? So that means that if you can't draw it out, it'll look like this. For one of okay, let me actually mix up the color real quick. Okay, so let's say we have red, we have blue, and then the destination is the pink, right? And then the red, now you can see that, we draw through this node. There's only one path, right? One simple path anyway. And then the blue one, you would look at like something like this, right? And that will be your graph, right? So then now for me, knowing this is just, okay, that means that we have to try to figure out how to, we have to find a couple of things, right? We have to find this red distance, the blue distance, and then also the overlapping distance, right? And once we have that, then we can figure it out. But okay, so first we're trying to get the distance between any 2 nodes on the tree. So okay, so I was like, okay, I need to know how to get distance between any 2 nodes on the tree. But given that it's a tree, there's actually a known algorithm, right? It's actually we'll go with this in more detail as I get into it, but I want to focus on the graph parts first. But basically the idea, but for me, I knew that the existence of this, and I knew how to do, I know how to do this. I'm just not explaining that part right now because for me, I'm explaining my thought process on how I attack and solve this problem. And for me, I was like, okay, I can do this, so that's fine. But just to kind of give you a little bit of a taste, is that yeah, so like let's say you have a tree. Right. right? So then the distance between two nodes, it's actually it's actually a very similar idea. Is that okay? Let's say you're trying to find this path, right? Well, this path is just equal to this path minus this what is it? And this path, right? Some combination of them. Maybe it's minus, right? Right? And that's really it. And then now, suffice to say that here, so because now you're able to get so now you don't have to do anything n square. You have to do anything from O to n, right? Because here, I'm not, like I said, I'm not going into detail yet. But here you can just calculate from the root to the node, the distance, to calculate this graph exactly, right? Okay, so then now let's say that as a result, we are able, okay, but I mean this graph doesn't show it. So let's go back to this graph here, right? So as a result, we are able to get the red distance, and we're able to get the blue distance, right? So then now, how do I solve for the overlap distance? That is the tricky part, right? Well, here we have the visualization, and this is why actually during the contest I drew it out. I drew out a different one, but a different graph, but the idea here, and I'll draw this more accurate, but you know, you have something like this, you have something like this for this one. Then what is how do you calculate this one, right? Well, it's pretty simple, right? Well, it's not simple, but the visualization is just, let me actually change the color for the overlap real quick. And we're trying to calculate the overlap, right? Well, if you kind of just add them together, then what happens? If you add them together, then the overlap, you have one part of this, one part of this, and then the overlap, we have two parts of the overlap, right? So kind of, if you want to draw it out, you have this part plus this part plus the overlap, right? So I mean, I drew it twice, maybe in a poor way, but so this is equal to this thing, right? So then to calculate this overlap, I thought I changed the colors. So to calculate this overlap, we just kind of do regular math, which is this overlap, we subtract this. I mean, I'm not going to draw it again because I'm running out of space, but it's equal to this part, we subtract this part from both sides, and then that's it, right? So then the overlap would be equal to, I should draw this out, but I'm not. Okay, let me just do magic, right? So then now, okay, well, you get the idea, right? Right, so we subtract this from both sides, and then we get the overlap. And then how do we get, well, this stuff we already told you how to get, right? Because we have this path, which is just the same thing as we do here. I mean, we abstract it for now. We know how to get that path. The blue part, we know how to get that path, as we already said. So this is a number, we just add them two together, and then we have to subtract this part, right? Well, here we can just subtract. Well, in this particular case, I guess this goes to the root, but technically you don't. All right, let me redraw this because I think with this it goes to the root, so it's not a great example per se. But let's say you have another example, right? You have another example where you have a node like this, right? And then we go like this, right? And you can think of this another way, but yeah, right. But the idea is still the same thing, is that, okay, you have this edge, you have this edge, so if you have this plus this, is equal to, yeah, right? Or if you're trying to get the overlap, which is this part, then it's just the overlap is equal to this part plus this part minus this part, right? So that means that we are just trying to get the path from this node to this node. And that's it. So then the overlap, 2 times this overlap, is equal to the sum of the red line, the sum of, and the blue line, minus the the distance from the red node to the blue node, right? As I said, let's say you're given the magic function to know all that, then that's all that is. And that's what I have in my notebook, is that you can't draw it out. And then you have kind of this thing as a visualization. Feel free to draw it your own, right? Okay. So then now, let's say that now we know how to get this answer, right? That's it. And then here, for this one, as I said, this is kind of well known because then now you could just do a depth first search to get a node, to get the you could do a search to get a depth first search, a recursive algorithm to just get the distance from the node to every other node, right? So that's linear time. And then now once you do that, then you just have to calculate. The red is trivial because that's just, you store it on this node. The pink is trivial. Was it purple? The purple pinkish is trivial because it's just to this node. And then now you have to get the LCA, right? And that's basically the core part, because given the LCA, then now the math is such that it's just the red, then the blue path is just equal to the red path plus the purple path minus the overlaps, right? Something like that, 2 times the overlap, because in this case you overlap twice, so you just have to subtract this thing twice, right? And that's basically it. Feel free to kind of pause and like draw it again or something, but yeah. Binary lifting. I forgot to explain the binary lifting. So okay, so let's say you get all this an idea. Then now the question is, how do you get the LCA in a quick time? And the way that you get the LCA, because you can think of the lazy way to get the LCA, of course, is that actually let me just redraw this. It's fine, right? The quick way to get the the naive way to get the LCA is that we can pre-process this with a thing, right? So here we pre-process it with a traversal going like right? And basically, once you pre-process it this way, a node for any two nodes, an ancestor is if a node is if, sorry, give me a second. A node is in another node's subgraph, subtree, lower subtree, if during this traversal, it comes up, it kind of enwraps it, right? Because if you kind of look at the timeline, if you look at the timeline of when we visit this node, and then we visit this node, then we visit this node, then we exit from this node, enter this node, exit from this node, and then exit from this node, right? So then as a result, you can see that all its subtrees will have entered and exited before this one exited, right? So that's basically the idea. And then given that, now that you have this function of whether a node is each is another node's ancestor, then to calculate the LCA of two nodes, let's just say this one and this one, the LCA would be that we take one of the node, and then we go, okay, am I the ancestor of the other node? Nope. So then I go up to the parent. Is the parent an ancestor? Nope. Is the parent of that an ancestor? Nope. Is the parent of that an ancestor? Yes. So then now this node is the LCA, right? So you just go one at a time. Binary lifting is just a way to make it so that it's kind of like a binary search or a binary walk, where you basically, instead of going one step at a time, you go powers of 2 steps at a time, right? Because let's say the lowest common ancestor is here, right? And here it's going to be, say, I don't know, some number 7 steps, say, right? Let's just say 14 steps is a random number. So then now, if you do it, and then now you just try to figure out how many steps you need to get it. And if you do power of steps check, then now you're doing, okay, is it 16 steps away? No. right? 16 steps will be the ancestor, so 16 steps is enough. So that means that we know that it'll be fewer than 16, right? Or 16 or fewer. And then now you try 8. Well, 8, we know that it takes 14 steps, so we know 8 is not enough. So then we know that it's between 8 and 16. So then now, and to check that, we move the node 8 steps, because then now we can just check between 0 to 8 after moving 8 steps. So I know that I'm not going into this detail enough, but I just want to give you a taste of what the binary lifting is. Definitely there are videos on YouTube that go over binary lifting and the binary walk, and also just LCA in general, right? Like, I want to give you a taste to kind of give you the idea of how my thought process is into solving this. And I solve this not using like, because I think sometimes I get this question of like, how do you know that you need binary lifting or sparse table or whatever, right? And I go, I don't know. I don't always go, okay, this is a binary lifting problem, right? I don't do that. I go, okay, I create the visualization that you saw with the nodes and the graph and the overlaps and everything. So I go, okay, but if I need to solve this, how do I solve it? Well, I need to solve this by using this other thing. And then this other thing, the way that I solve it is by binary lifting, because this is actually, honestly, if you deconstruct it in that way, it is a standard binary lifting, it's a standard LCA problem that requires binary lifting to solve, right? Because complexity is that you need to solve it fast, n squared is not fast enough, so you need n log n LCA, and that is done with binary lifting. Also, there's an O of n LCA, but I'm not going to get into that for this problem. And it's not necessary, obviously, otherwise we would be talking about. But yeah, here's the code part. I'm not going to go over it in detail because you can just probably, like I said, Google in detail how it is. And I think also, honestly, many people have templates for this. And frankly, I don't know if this is true, but you could probably ask ChatGPT and it'll give you a template for this. I didn't do it that way, which is why I ended up taking 25 minutes. But if you had the template or ask ChatGPT for a good template, you probably could get this in 5 minutes if you have the other understanding, right? So I'm not going to go over this in detail, even though I will show it to you in case you're curious. But yeah, so here in the go function where we just process each node, first we have the timer thing that I talked about, and this kind of does the depth first search traversal of the tree, right? Which this sets us up for the ancestor part, and then this is the sparse table, right? You can say that parents I of x is 2 to the I steps up from x, right? We'll give the node that is to the, so like if I is 0, that's 1 step up. I is 1, 2 steps up. I is 3, 8 steps up, or 4, whatever, you get, maybe I skipped the number, but you get what I mean. Yeah, and the way that you do this canonically is by dynamic programming, because basically the way that you think about constructing this in an easy way is that, okay, let's say you want to calculate the thing, because this is 2 to the I, right? So let's say 2 to the I is 8. Well, instead of doing 8 1 steps, you combine them into 4 2 steps, and then combine those 2 steps to 2 4 steps, and then now the 2 4 steps you can combine to 1 8 step, right? So that's basically what this is doing. It's just doing because basically okay. So in that way, if I is make it so that it's 8 steps, then 4 steps away, it's going to be this node, right? So this node gives you 4 steps away, and then now 4 steps away, you want that 4 steps away. So then that's how you get a kind of recursive looking thing, which looks really confusing when you put it in one way and you haven't been used to it. Otherwise, everything is pretty straightforward. Also at the same time, we also pre-process the distance from the root node. We root it at 0. It doesn't really matter because you can draw the geometry math in any way. And yeah, and then we have an ancestor, right? Again, we briefly touched about it. We're not going to talk about it here. The LCA, we also briefly touched about this. We're not going to talk about it because this is standard-ish. So it took me a little bit of debugging because I kind of messed up the order a little bit, but so that's why, part of why I was slow. But yeah, and then now we have the distance, right? So this is distance between node 1 and node 2. And the distance between node 1 and node 2 is just root to node 1 plus root to node 2 minus 2 times the overlap, right? Where LCA, and oh yeah, the LCA part. So the root to the LCA is the overlap, right? So then this is just 2 times the overlap because we overlap it twice, right? You could draw it out to kind of see this visualization, right? Oh, I guess I. And then for each query, we have the same thing, right? Same idea, not the same thing. It's the formula is different, right? But yeah, so we have, yeah. I mean, you could read this. This is pretty readable, I think. You have the first distance, the second distance, and then the direct route, in which now we can calculate the overlap. The overlap is just d1 plus d2 minus the direct route over 2 because when you sum it up, you have two of the overlaps. So one of the overlap is this, and you do want to keep one of the overlaps, so it's just this, right? And that's it. Yeah, I mean, as you can see, me explaining this part is just like 5 minutes if you have the visualization, right? Or not even 5 minutes, but like very fast once you have the visualization and everything's good. So complexity, right? So complexity, like I said, you could use this as a black box, but it's gonna be n log n, log n per each query for the LCA query. This log n because m is gonna be, well, I guess it's not log m. No, I guess it is log m, right? I mean, I did it 18 because I hard coded it to 18 because I didn't want to do log n. I was a little bit lazy. But I guess log n would have been fine. But yeah. Because I always worry about off by ones when it comes to log stuff. It's just bad habit maybe. But in any case, yeah. So this is, let's say this is log n, and yeah, and this is O of 1 because as you can see, this is just an if statement, right? So log n for each LCA query, right? So the distance, which means that the distance will, this is log n, but this is O of 1, right? So that means that, yeah, and this formula is also O of 1. So that means that the distance function is log n. And yeah, and that means that for each query, so this is going to be q times log n, right? Time and O of q space, right? Because for each, and we do pre-process this, right? And the pre-processing part is only linear, right? Actually, no, I lied. It's n log n because of this part. This part makes it n log n. M is log m. So pre-processing time. And then now this is going to be time and space because we do 3 log n operations. And then everything else is O of 1, right? So that means that the total complexity is going to be O of n log n plus q log n time. And then O of q, n plus q space, right? N log n space, I forgot, sorry. It's a sparse table, essentially, with this parents thing, with binary lifting. And that's it. That's all I have with this one. Yeah, let me know what you think. Let me show you the code real quick, now that you have it. I construct the edge list, the adjacency list. I pre-process the table in 3 ways, right? The binary lifting parents, the LCA timer, or the ancestor timer thing, and then the distance to the root. There is ancestor function, what we talked about. LCA, also what we talked about with the binary search. Again, if the LCA part isn't clear, there are videos, so check that out. This is the part where we drew the visualization with the graphs. I think, yeah, if you drew it out, it'll be more clear if you don't understand this part. This part, the same thing, right? Just draw it out, and you can kind of reason it, the components and how we come in, right? And that's it. That's all I have for this one. Let me know what you think. Thanks for watching, and you can watch me solve it live in the contest now. We'll submit. Come on, no wrong answers. Okay, good. Okay, let's not linger. Q4. How am I doing on ranking so far? Ooh, not great. A lot of people got Q4 very quickly. I guess I'm doing this quickly, so I guess they haven't removed the cheaters yet. But still. Okay, you're given an undirected tree, so the n-1. Okay, it's a undirected weighted tree. Okay, that's just setting it up. 2D arrays, you have query, source, destination, minimum total weight of subtree. Okay, so it's rooted. Is it always rooted at 0? What does this mean? Okay, they're using the definition of subtree. That's a little bit confusing, but maybe that's fine. What is the thing again? 2, 3. So basically, it's just like 0.2. I mean, it's just like the whatchamacallit. Just combine the trees or whatever, right? Or to combine the paths. This is 7 pointer. How much time do I have left? An hour. And that was a mess. Okay, well, I guess you can't tell anything from people cheating anyway. But, and that's why I don't do these live anymore. 0 and 2 to 5, okay. Okay, okay. I mean, binary, whatchamacallit, is it binary lifting? Binary lifting is going to get you the 1 query answer, and 2. Is it just... What does getting source 1 to source 2 get you? It should be able to... So, okay, so then now you have this. Yeah, okay, I mean, it's just 3 binary lifting queries, right? I mean, I have to write the binary lifting, but I don't think that's that bad. You just do the math. With the visualization, it's just from source 1 to destination plus source 2 to destination. And then the dupe is source 1 to source 3, or source 2. Right? Minus the... Wait, what? Okay. Draw it again. Okay, so you want this, and you want this. So that gives you the duplicate, and then now you have this. So then it's just minus this. Will give you 2 times whatever. So then now to divide by 2 will give you the extra duplicate part. And then yeah, that's it, right? Okay. Not too bad. We'll see. I haven't done binary lifting in a while, so we'll see whether I can actually implement it. But the idea is not that bad. Okay, right. Would it add, say, 0? Or LCA? When you get distance between 2 things again? What's it called? Okay. How do I get LCA again in binary lifting? I mean, okay, fine. Okay. Is that the Cartesian traversal or whatever? No, not the Cartesian tree. Maybe. But it's just a depth first. So then the LCA is oh yeah, then you binary, not binary search, but then you walk to determine the thing. Okay, fine. Okay, fine. Okay, yeah. Okay, fine. Something like what's the default value? I guess it doesn't matter. Oh, no. This is the time step. Then we have, what's it called? Time in, time out. I always forget if it's plus n is equal to edges plus 1. Okay, weird spacing now. Right. Yeah, okay. Okay, right. So then now I think that's right, right? Actually, I don't know. It's fine. Go reload. Okay, so there we go. And then now its ancestor is just okay. It's something like no possible ancestor. So it is an answer. Which way does it go? I don't even remember. Return time in of node. So if it's the ancestor, it gets in first and out. Yeah, right. So okay, so time in. Time in. I guess it cannot. I guess it could be equal if it was the same node, which is trivial. Okay, right? Something like that. Though maybe it's more precise to write. No, can that? I guess maybe it's possible. I don't know. I don't think that's. Oh right, yeah. If it's not the same subtree. Okay, fine. Okay, and then now we just do the LCA, right? So to find the thing, we find LCA, and then path to the root. Okay, fine. I have to add something to this as well, so that's the distance, right? From the root. I didn't even call it, so maybe I need to call it 0, -1, 0. D, right? So then now distances of node is equal to D. We go D plus W. What's the W? All right, let's see if this runs real quick. Okay, looks okay. I mean, it doesn't crash. I guess I got print stuff. That part I'm not worried about. I mean, this part I've done a billion times, so I've also failed a billion times, so I don't know. Okay, and then now LCA, node 1, node 2, right? Then now, how do we do it? Oh yeah, okay, so then if potential ancestor, so then return node 2. If node 1, and then this part I always struggle with. Oh, I didn't pre-process the nodes, right? So okay, so okay, how do I write this? Let's just do 20. Is that reasonable? What's 2 to the 18? Maybe I could be a little bit tighter. 2 to the 17. Let's just do 18, right? And then we have I wouldn't go pass. I don't know. Actually, I don't know. Yeah, I guess that makes sense actually. Okay, fine. All right, and then now, I guess here we know the parent. So then here we go. This isn't quite right. I don't want to write it this way. Okay, so parent of, oh man, this is terrible naming. Okay, fine. Parents of 0 of node is equal to node, so that's 0 steps. No, that's 1. Let's keep it 1 step. Right, so then this is parent. And then for I in range of m, starting going to 1, and parent sub I of node is equal to parents I minus 1 of node, and then this gives me the node, so then okay, something like that, right? Okay, print parents. Okay, that's why I want to run it. Not none type. Oh, it's none. Okay, so we don't set it up for 0. That's why. No, it's 0. Oh, because it's just -1. Yeah, which is true. That should be fine. Oh, because then this is -1 as a reason, or something like that. Oh, this is well, okay, one of them is -1. I see. How do I want to write that? I mean, I just want to set it to the root, right? So, yeah, I don't know if this comes back to bite me if I just choose 0. But I guess for now it's fine. Okay, so no, that's okay. So that's the parent on the 0th level. 2, 3, 4, and then 2. Okay, and then this is 2 steps. It's 1, and then the next one should be 0. Okay, I think this is right-ish. Okay. It's been a while. I guess people have templates for this, but it is what it is. Okay, so then now we Okay, so for I in range from m minus 1 minus 1 to 3, right? So then now we go, okay, if parent sub I of, is it node 1? This doesn't really matter, right? Node 1, if something like this, what does that mean? So that means if the root is an ancestor, okay, so, but we want the opposite of that. So if this is not an ancestor, then we travel, right? So, okay, so then now node 1 is equal to, okay, right? So then now if it is, then you don't travel. Right now we turn node 1 or parent of node 1. Man, I should have template for this. Okay, we can print out some quick ones. Okay, let's see. 2 and 3, say. And then maybe 2 and 5. 2, 5, 4, 5. Alright. I mean, it's going to be one time error, so 0 is the root for 2 and 3. That's not right. It should be 1, 2, 5. It's 2, that's right, but that's I think a default thing here. And then 4, 5 is 0 is also not right, so Okay, let me think. Okay, so how much time do I have left? 46 minutes, that's fine. Okay, so I'm debugging people code that people have template for is a little bit sad. Okay, so it's, if this is not the ancestor with this step, we have to get it. Okay, that's fine. Okay. Yeah, that's fine. So then, what if it is? Okay, if it is, then we don't. So we go back. So we find the one, maybe. But I don't. I want to say maybe it's this, but I don't see how that would change anything because it's just zeros, right? So there's something wrong here. Did I set this up wrong? No. 1, right? This is so annoying. Node 1, node 2, parents I node 1. I guess it doesn't really help if I don't find out the result. Okay, so the zeros, what am I putting? Between 2 and 3? 2 and 3. I parents, okay, so it thinks it's false, that's why, and it goes to 0. So the false part is really wrong. But why is 0 false? Oh, I did it the other way, I think. Okay. Because, yeah, okay, fine. 2, 2, 4. Okay, then now I think this is more reasonable to be this. I thought maybe it's that, because you want to get the one, the last one that isn't that. But yeah, 1, 2, 1, okay. Now we're Gucci, I think. Okay, so then now we can do the math. Okay, so then now distance between two nodes, what is it? is going to be equal to okay, LCA is of node 1, node 2. So meet, maybe, I don't know. So then now we have what do we call distances. So yeah, it's going to be return distances of node 1 plus distances of node 2. This double counts distances of meet, and then there you go, right? So then now we can get distances from, oh, we have to enter the queries. I forgot that we have queries, it's not just one. Okay, how the query structured? Okay, for I don't know, whatever, S1, S2, D destination in queries. Okay, we want to say, I don't know, whatever for now. This distances from S1. I think we're close now. I guess that's, I mean, I think even if you have templates, if you had templates, I could see how anyone get this pretty quickly. Okay, so 9 and 11, is that right? S1 to S2. What's the query? 2 to 3, 2 to 4 is 7. That's not right. 3 to 4 is 9. Maybe not right. Why is that? Okay, S1. Just making sure that I'm looking at the right thing. Okay, 2 to 4 is not. Oh. 2 to 4 is 9. That's not right. Okay, so then here, then 2. Me. Okay, so we want to go from 2 to 4. Distance is 5 and 6. Is that right? 5 and 6. That's right. And then meet is going to be, they meet at 1. Distance 1 is 2. So then now, oh, distance from 2 to 4 is not 2. It's going to be 2 times that. Okay, because it's not. I've confused the problems. Okay, fine. I see. So yeah, 7, 9, 0, 5 is 11. That just makes sense. 2, 5 is 6. 2, where's the 5? Oh, 6, yeah, okay. Okay, so then now I feel like this is right. And then now we have these two distances. Do you want to D2 is equal distance S2, right? And then now if you sum up together, you would double count the overlap, and the overlap is just it's not the LCA, though it is similar in idea. Oh no! You did this. You did the math. Okay, so then the overlap is 2 times the overlap is equal to the distance from S1 to S2. No, this is not overlap, but direct maybe. Okay. I'm looking at my notebook in case anyone's curious, because I drew this out. So then now, so if you sum it, then you have that, and then the overlap is the direct. So then the overlap is equal to D1 plus D2 minus direct over 2. This part, the part that feels weird is that this has to be even, so, which would be weird for this problem, I think so. But it's a little, given the constraints, but it feels awkward that that's the case. So. Let's let's run it real quick. I guess that looks right. Okay, so then now it's just minus overlap once, and then that's it, right? 12, 11, and 15. Okay. I mean, definitely possible that we're making a silliness somewhere, but I feel like this is okay. So let's give a YOLO submit. Okay. Whew. Yeah, I mean, I don't think it was a tough problem. It was just, like, it's very templateable. If I had templates, it probably honestly is like a 5-minute problem for Q4, even without ChatGPT. But thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, explanation, everything in between. Stay good, stay healthy, to mental health. I'll see y'all later and take care. Bye bye.